Let's talk about time-dependent problems. So there's kind of two choices. One choice would be a coupled approach. And in this case, you have some unknown u, some solution u, that's a function of space and time. And we would approximate that some unknown coefficients uj times some shape functions that are both functions of space and time. Okay. This is not very common. In fact, I'd go as far to probably say it's unheard of outside of academia. There are some sort of academic research areas and codes that use this type of discretization, but there's no commercial code, or really even no popular open source codes that implement this sort of time-dependent shape functions. And the reason is it's really not that useful. I mean, the reason we need finite elements in space is because we solve boundary value problems, right? We have, you know, we sort of have, in an arbitrary way, boundary values, and so we need the spatial discretization, right, for the boundary values. But for time-dependent problems, it's very rare that we know the state at the beginning and the end, right? We usually just know it at the beginning, right? We don't know it on the boundaries. We just know it at the beginning, right? And so it makes more sense to sort of take a sequential in time discretization where we start and we solve an initial value problem in time. So we start with some known conditions at time t equals 0, and then we just march forward in time. Okay? And so that's the sort of more popular method, and the method that we'll use is a decoupled approach, and that is separable. So in this case, we have some unknown solution u that's a function of space and time, and we're going to approximate it, u of h, where we have now some unknown coefficients that are functions of time and our standard spatial shape functions. Right. And this follows from the same ideas when, if you've anybody ever had a course in PDEs? Or a graduate course where you covered PDEs at all? So there's about 3 PDEs in the whole world that you can solve in closed form, right? And what method do you use on every one of them? Separation of variables, right? So, you know, it's the idea that you can separate the solution into independent functions of space and time and multiply them together, right? That's not the only way. There's a few other ways to solve a PDE, namely like method of characteristics and other things. But for the most part, this is the method of attack when you are faced with solving a PDE analytically. Yeah. So we're going to do a spatial approximate with finite elements. And do a temporal approximation with something, right? Finite differences, essentially. Some form of finite differences. So that is, you know, we're going to approximate this time dependence, the time derivative du dt, with some increment in u or some increment in t. And so we have 2 general classes of time-dependent methods, explicit and implicit, right? And you probably have covered some of this in other classes, but I just want to go through a very generic look at both methods, explicit and implicit, and look at some of the properties of each of them. So we'll just start. If we have a generic differential equation that some function of x dx dt is equal, and I'll just use the time derivative, the dot notation for time derivative. We've already done that in the class, but just to be clear. Is some function of x and t, right? We're going to discretize time into increments at t0 plus delta t, t0 plus 2 delta t, etc. And so then when we do that, we'll have that x dot at a step in time is equal to f xn tn. Right. And so, again, when we discretize the derivative using this sort of delta x delta t approach, we'll write x n plus 1 minus xn over delta t. Okay, that's equal to our function of tn xn. So therefore, xn plus 1, solving for xn plus 1, is xn plus delta t f xn xn tn. Okay. And if we allow x0, the 0 time step to be equal some constant, then we can write x1. And, by the way, this is the reason this is explicit, right? If you look up explicit in the dictionary, it means to write down plainly, right? So we write this, this is written down plainly because everything on the right-hand side are things we know. Okay? Things at the nth time step. We're solving for things at the n plus 1 time step, but it's all a function of things we know, things we already have in our hand. Because at, when n equals 0, those are initial conditions. We know those. Right? We have to solve the problem. And then so in every, the first time step we can compute from what we know, and then those become our next time step, and we know that, and we just iterate, right?
How do you know f at the first time step?
At the first time step, so I made a choice to say that it's a function of xn and tn, and in a minute I'll make a different choice, okay? But for now, I guess I should have made that clear. I could have said xn plus 1, but in the explicit case, I made a choice and I said, okay, we know we're going to assume that the function is a function of xn, right? Well, at n equals 0, or time step t equals 0, at time step 0, we know the spatial configuration, right? So we know, well, assuming x is a spatial variable, we know it.
Right below, then you said x n plus 1 minus x n.
Yeah, so there I'm discretizing the time derivative. Yeah, I probably shouldn't use, that shouldn't be x. I should miss the, sorry. So, actually, in both cases, sorry. Yeah. So, yeah, so, here I made a choice also about how to discretize the time derivative, such that the choice resulted in something that's explicit. We'll see something that's not explicit in a second. But that choice resulted in this equation. So in that case, I know everything, right? So if we just write down a sequence of solutions, so assuming that x0 is equal to some constant, so this is how we write down the sequence of solutions, right? This is all things we know. If time t equals 0, we just plug them in and compute x1. Now we have x1, we plug it in here. We have x2, and we just keep going. Okay? So let's look at some characteristics of this method. And one of the things let's look at a specific choice of the function on the right-hand side. So if we have this differential equation, and where x0 is equal to c, well, we actually know the solution to that differential equation from your first day of differential equation class, right? Is the solution to that is x to the t c e to the lambda t, right? The solution to all linear differential equations is e to the lambda t, essentially. If I ask you to ever solve a differential equation, right? You can write any. If you're given a 100th order differential equation, right? You can write that as a system of first order differential equations. And as long as they're linear, then you have some A matrix, right? The solution is always, e to the AT. The trick is computing e to the A, right, where A is a matrix. It's easy here. So we know that this solution will only be stable if the real part of lambda, because lambda in general could be an imaginary number, the real part of lambda is less than or equal to 0. Right, so lambda has to be a negative number for this to not grow to infinity, right? So if we look at that explicit discretization of this equation, we have this, which is equal to and if we continue to take time steps, the next time step we'd have such that eventually we'd have by just continually plugging in the answers, ultimately we'll have this guy. That's x0. So in order for this to have a stable solution, the absolute value of 1 plus lambda delta t must be less than or equal to 1. And so therefore you can solve for delta t So delta t must be less than or equal to 2 over the absolute value of lambda for this to have a stable solution. So an explicit method has the stability criteria. And this can be fairly restrictive because, you know, if we think about a mechanics problem, if you think about a mechanics problem, these lambdas, they turn out that they're eigenvalues of the problem. They're like the fundamental frequencies, right? And so essentially what this implies is that the time step must be small enough such that it can capture the frequency or be able to capture the propagation of a wave across an element. And, you know, when I say wave, I'm talking about like the wave speed of a material. The longitudinal wave speed is like the Young's modulus over the density. So for a material like steel, talking this number is like 50/50, so 5,050 meters per second for steel. And so that's pretty fast, right? So imagine you're going to, you know, what steel and things we use are like drill bits, right? So imagine you're going to do a finite element approximation of a drill bit, and you're, you know, what size mesh do you need to accurately recover, you know, to accurately recover stresses and strains in a drill bit? You know, they're probably on the order of let's just for ease of math, let's say a millimeter, right? So you need characteristic element sizes. In order to discretize a drill bit accurately, you probably need characteristic element sizes on the order of a millimeter, right? And so you have to be able to, your time step has to be small enough that you can capture a wave going across this millimeter size element, and that wave travels 5,050 meters per second. So what it turns out, your delta t there is something like on the order of, your stable time step for that scenario is something like 1 e to the minus 7th or 8th seconds, right? And you want to do a drilling simulation that lasts 60 days. Good luck. Taking steps of 1 e to the minus 7th. Not going to get very far. So while it's great to have a method that's so easy to implement, you know, for very few scenarios is it really useful. Turns out that one of the useful scenarios that I used to work in that area is impact. So in car crash, you know, in penetration mechanics, where the entire event may only be 6 milliseconds, then this is the method of choice because it's very robust and it's fast. So for an implicit method, so in this case, we're going to let our time derivative be so previously we had x to the n plus 1 minus x to the n. Now we have x to the n minus x to the n minus 1. And if we plug that in, to our equation, then we have this. Solving for x to the n, we have this. But we don't want x to the n. I mean, x to the n is the time step we're on. Right? We want the next time step. So n plus 1. So we're just going to add plus 1 to all the n's. So then we'll have n plus 1 equals to f x the n plus 1. So this is the old time step. These are values at the current time step, and you see they appear on both sides of the equation. So this is an implicit method. It's not written down plainly, right? And if this is a linear problem, then it means we have to invert a matrix. If it's a nonlinear problem, we can't solve it without some Newton iteration. When I say nonlinear problem, I'm saying that f, whatever the function of x and t is, if it's linear, then we can solve this by inverting a matrix. But if it's nonlinear, you had an x squared in there, then you'd have to use some Newton iteration, which would also involve, at every iteration, inverting a matrix. Because we're going to linearize it first and take a step. So if we analyze that same problem that we x dot lambda e to the xt with this method, moving everything that it with xn plus 1 to the left-hand side. So this is stable if the absolute value of this is greater than or equal to 1. I guess. So this as long as, so this is, as long as delta t's are, well, as long as delta t's are positive numbers, this is always greater than 1. And therefore it's unconditionally stable. So you can take any size delta t and it'll have a stable solution. So when I say stable, I mean the errors don't grow unbounded, right? And this isn't true. This is just 1D. I mean, this extends to multiple dimensions. However, this is only true for linear problems. Okay. So we don't really have a great theory, a general theory for nonlinear problems. So a lot of times, what we do is we use the theory from, like specifically in the explicit case, it's the same thing. We have that critical time step calculation, but it's only valid for linear problems. So what we'll do a lot of times is we'll compute it for a linear problem, and then because we really have a nonlinear problem, we just put a safety factor on it. So you compute the critical time step, and then you might, usually something like 80% of that, so you have some reduction. That doesn't mean your simulation won't go unstable at some point. Sometimes it does. And I've had it happen to me. Particularly in impact problems, where you have a lot of compression, right? And so you have this characteristic element length, right? And you start with the elements this size, and then you're slamming it, you're compressing it, and at some point, it becomes smaller than the characteristic element length because it's shortening, causes your time step criterion to be violated, and then your simulation will go unstable. So in a second, we'll talk about a way where we can hopefully identify that.